So we're gonna talk about space architecture and what architecture can bring upon designing on space. To be able to start this discussion, I would like to first tell two little stories. One of them is from Soviets in early 60s, that the plans were getting involving having more people for more durations in space, and therefore some habitation parts, some habitation modules were needed, and therefore the designs were made, and it was just two red boxes to mark the places that humans gonna live. So the design director on that time thought that it would be nice to have an architect involved to make the place habitable for humans for longer durations. Then Galina Balashova can be referred as the first space architect. It was involved in the designs and continued her work for decades. And another similar story is from Skylab, this time from America, this time in late 60s and early 70s. At that time, Skylab was gonna go to space to be a space laboratory. Therefore, people were gonna stay there in much longer durations than ever have been tried. And in this manner, the habitation model should be bigger and more suitable for humans. Thus, they also, because adding the other considerations, they decided to use a propellant tank, and they have almost nothing inside it to make the living easier or tolerable in that can. And even the astronauts who are gonna live there seems not to care about it. And later, this time again, a mission director thought that a designer is needed to fix the interiors at the very late parts of the project. Thus, the firm of Raymond Loewy is involved, and they made a lot of research, and they designed the interior for human living. And you can see the astronauts mentioning of the space, talking about the space in all their talks recorded there. For example, the window was the thing they were just always going in front of. They were using this wardroom to be together and have meals together, etc. They were even complaining about the colors. The people who didn't even care a little about going what kind of place they are going, because they were survivor soldiers. They were now very interested about that when they are living in it. So space architecture is a very newly examined project, emerging project. I'm sorry. And it is defined as the theory and practice of designing and building inhabited environments in outer space, responding to the deep human drive to explore and occupy new places. In a congress done with the architects gathered together in 2002. So what are the design considerations? What do we need to consider when we are designing for space? To start with, it's an extreme environment, and it shares the characteristics of extreme environments, which is hardship of reach, autonomy, isolation and confinement, lack of external stimuli, social monotony, lack of resources, and hardship of evacuation in case of emergency. A lot of extreme environments share those specific characteristics. It may be in desert, it may be in ocean, but in space you see all those things at the edge. In moon, we have this kind of we don't have a communication delay. For example, we still see the Earth, and we can evacuate moon and go back to Earth in a while. But in Mars, that won't be possible. So in space, also the places we go changes the discussion. So as architects, we try to look into human environment interaction, and in space, it is also done this way while designing for humans. It could be referred as environmental psychology, human factors, or ergonomics, or habitability, but they all are working on the same subject of human environment interaction. So we can This is Elizabeth Lockhart's levels of human habitation of space. First one is survival, in which you just need to protect human from the other things like radiation, or give them the air to breathe, but you don't expect them to do a lot of things, which were the first space missions. Performance is where you expect the human inside to do some tasks, to be able to do some tasks. Therefore, you give a little bit more to them. Those were the following missions of space. And now today we are in the habitation phase. And at that phase, we expect this habitat to have all aspects of living in it. It could maintain all those things. And adaptation is a long to come subject, but it's more discussed in both ways. It could either change the planet to make it fit to us, or terraforming, or it can be discussed to change human to fit Mars environmental conditions, which is long to come subject. But we are now in a habitation phase, and we are going towards the adaptation maybe centuries from now. And we should consider all today's and tomorrow's technologies in mind. So what do we consider when we are designing for space? First of all, the distance of the planet or the destination point, and the movement and cycles of either the vehicle or the planet are important. And again, on the other side, the conditions on the planet or vacuum, I don't know, is important. And on the human side, we can talk about first survival and orientation and movement and circadian rhythms to help people survive, and then we should deal with their psychological conditions and take care. We need to answer those questions with the habitats, and also the type of the user and the amount of the user. Those kind of stuff change the type of the habitat and what is expected. So if we see the habitat as the to respond both ends, it may have many qualities to respond to these things separately. If we need to give an example, for example, if we take lighting, lighting could could be both important for human circadian rhythms, and also it can be used for like private and common places separation, etc. There are many things that are interrelated. Sorry. And on the other hand, we need to respond to the environmental conditions as well. In addition, the design process is important when we are designing for that. For example, we need to be able to somehow have some information from past, or with our experiments, like as we do in Habitat Marte now, we can gather some experience through Earth, and we don't have anyone to try it. We don't have anywhere else to try it first. So we need to somehow provide a design that we can try it here first. On the other hand, not only today's technology, but tomorrow's technology should be considered while designing for that, because the project span is not very small. So we should consider what can be developed until we start to execute the project. And on the other hand, we care about spin-in and spin-off, because we need some money to do stuff there, and if we don't provide those things, it becomes harder to get. So if we get our focus in Mars environment, for our project, what should be the considerations? this time we know the distance and the cycles of Mars, which is not so far away or foreign from Earth. We have still a similar 24-hour day and like 2 years of a year, but we have a light cycle and we have lesser gravity, but we have gravity and we have some resources there. And the biggest problem might be there is radiation and the hardship of reach. And the atmospheric pressure is also very important. We are designing to deal with the pressure, not the gravity, as we do on Earth. So what are some projects, what are some examples we have until now? I'm gonna give the speech to Sima.
Thank you. And now we were focusing on some design examples on Mars. We have chosen 5 examples for like, because some of them are printed with 3Ds and some of them are just astronauts are going there and building it, like modular designs. And firstly, we're going to focus on Mars Ice House. After that, we're going to focus on Martia, Mars X House, Mars Incubator, and Hasselhoff. Mars Ice House was born from the imperative to bring light and a connection to the outdoors into the vocabulary of Martian architecture. The winning proposal stood out as one of the few entries, not to bury the habitat beneath regolith, instead, meaning the anticipated abundance of subsurface ice in the northern regions to create a thin, vertical ice shell capable of protecting the interior habitat from radiation while celebrating life above ground. And these are the levels. This is the first level we are seeing as a number 1, rover dog airlock here. And after that, we have an entry level. And we have kind of a yard here. And after that, when we look at the level 2, we are still seeing the yard. And here is a hygiene area. And this is the vertical greenhouse. So it's kind of not a narrow place, but like astronauts have also vertical spaces here too. The yard is an unprogrammed space between the inner habit and outer shell. This area is not for any specific function, but an undefined open space for contemplation, relaxation, exercise, gameplay, or anything the crew decides to do. While not fully conditioned, this space is pressurized and can be inhabited with a simple oxygen max. It also serves as a buffer space, absorbing leaks from the habitat environmental control and life support systems to minimize further contamination of the Martian wilderness. And this is the section of the building, and we are seeing the ice shell here, and this is the buffer zone that they were mentioning about it, and this is the yard. Water is a building block to life. The team used a follow the water approach to conceptualize, site, and construct their design. Formally, the project is deliberate in redefining the prevailing diagram for off-planet habitats. The prevailing precedent has been inflated domes covered by a layer of regolith, which yields dark and claustrophobic habitats with potentially disastrous consequences for crew motivation and mental health. And this is the vertical kind of garden that we had seen on the plot. This is Martia, and this is the 3D printed design. Martia is a first principles rethinking of what a Martian habitat could be, not another low-lying dome or confined, half-buried structure, but a bright, multi-level, further-free home that stands upright on the surface of Mars. Vast structures on Earth are designed permanently for gravity and wind. Martian conditions require a structure optimized to handle internal atmospheric pressure and thermal stresses. It takes less energy to process and print with water. This natural climatic and atmospheric conditions allow us to take advantage of the physics of phase transition. And this is the shape of the Martian, and this is how they were thinking on the shape of the Martian. And it's super strong because basalt fiber is known for its super tensile strength. It's comparable to carbon fiber and Kevlar, yet much simpler to produce. And it shields radiation. Due to their low overall atomic weight, plastics are effective shields for ionizing cosmic radiation, and it's renewable. PLA is a strong thermoplastic that's a recyclable and that has the benefit of means to manufacture. Dimensionally stable. PLA has the lowest coefficient of thermal expansion among plastics, crucial to achieving composite action with chocolate basal fiber, which is also highly stable. And it's non-toxic because being a bioplastic, emissions from PLA printing are clean, unlike petrochemical plastics which emit high levels of toxic microparticles such as tree, and it's non-conductive. PLA is prized for its low conductivity and basalt is among the most effective insulators now. Together they shield against the exterior environment. And Martian employs a unique dual shell sheen to isolate the habitable spaces from the structural stresses brought on by Mars's extreme temperature swings. Each level has at least one window, which together cover the full 360-degree panorama, indirect natural light from the large water-filled skylight, and intermittent windows block the interior while still keeping the crew safe from harmful solar and cosmic radiation. Circular lighting, designed to recreate earthly light, is employed to maximize crew height. And here we are seeing windows, and we have a little garden here. And we are seeing windows like the 360-degree panoramically around the structure. And this is a overlooking part. And this is an interior render from Martian Architecture, and we are seeing the shell from here. And this is another design, it's Mars X-House. It's version 1. X-House is the fourth prize winner of Virtual Design Level 1. 60% design within NASA Space 3 Habitat Challenge. Prioritizing safety, redundancy, and the well-being of the crew above the Martian surface, Mars X-House seeks to exceed current aviation standards while safely connecting the crew to natural light and views the natural landscape. And this is a section of it. Here that they can sleep, and they have shop, and they can also observe the around. X-House presents a pioneering capital scale to fit within the 4.5 footprint of the level 3 head-to-head event of the phase 3 competition at 1/3 scale. By literally connecting the human residence with views to the Martian landscape, the habitat synthesizes key design factors unknown to the future Martian habitation, program and construction efficiency, light and radiation protection, creating a highly functional and protected habitat for its occupants. Then this is the section of it. The density of Mars atmosphere around the horizon can allow light transmission up to 30 degrees above the horizon. This critical finding essentially enables a relaxation of constraints and supports architectural concepts featuring windows and apertures allowing visitors to the Martian surface. And this is the level 1 terrain. The foundation is 3D printed by two mobile construction printers. The inflatable modules deploy and connect the airlocks and sweep ports, followed by 3D printing of the regular shells protected by habitat and its interior. Mars X-House placed each laboratory space in separate redundant tables, yet connected at the same level and connected through a sweep port floor, which astronauts go on even and over expectations. And we are seeing labs, and they are airlocks, and they can pass through from these corridors and go on EVA and rover expeditions. In Mars X-House 1, the Hercules bandwidths are contained ESS systems, as well as the web functions, and connected to the insulated habitable areas through the connector node. And this is the fourth design, it's Mars Incubator. Team Gamma in 2015 won second place in NASA's 3D printed habitat challenge by using a semi-automated cable fabrication system, and this is called RAM. They created a protective shield around an inflatable modular structure, and we have a short video about it. And this is for an example of modular design. And this is the last example of the design successful in EOC. Aim was to bring a more human element to space design, typically all about maximum efficiency and performance. And they were thinking about with a creative view or a design view, you are able to solve very constrained problems. So there is a place for design and architecture in interplanetary habitation. And the shell is autonomously 3D printed layer by layer. And this is under the shell. The habitat is multi-use and reconfigurable. The design includes a hard shell which will be constructed entirely from Martian dust by a team of autonomous robots prior to the astronauts' arrival. This shell provides shelter that the astronauts can then construct their living quarters beneath using several inflatable pods. And after autonomous robots come, they are building modules like this. Inflatable pressure isopods are deployed and connected. And this is the scheme of the area. It's a place where they feel safe and equipped with the most important work in the history of space exploration.
Okay. We are other space architects, including some designer and architects and engineer friends. In the initial part, Ece made a general space architecture talk, and then Sima gave some examples, and lastly I will give our personal design. It's named Mirage House. We got some biomimicry inspiration from nature. We made like a two component of two biomimicry. One is this plant, and the second one is the honeycomb. This plant named spherical Fibonacci lattice. It has like a small flowers inside. So it's something like this when we take one of it. And in the honeycomb, as you know, hexagonal shape means that you can include more honey inside of it. So that's why it's like hexagonal. I combined these two and reached to this shape. So we use this shape to make our concept of design. In the computer, I was trying on it on this shape. When we continue to increasing the number of each panel, it can take us to the perfect sphere also, and it can be like a trusses like this. When we make it circular, it will be smaller in the top part and bigger in the bottom part. So we reached out to this shape. So this is our design, but I want to put more details what we have in concept and why we did like this. This spherical circular shape has two layers, and like two layers on each other, and in the middle part we press the air of the Mars itself. So in the previous, a lot of projects they did like ice shells or maybe something different, but we have a new idea about this, about space architecture projects. We wanted to take the air of the Mars itself and press it in the middle of two layered material to protect inside, to make safer inside livable part. As you can see here, these are the airlocks, or it can be like a passage to the other neighbor. It will be like neighbors next to each other. In the middle part, there will be livable area, safe area with different small neighbors. We have concept on the having like a small district, like a village project on the Mars Village project, and it can be like a greenhouse design, but habitats in it. This is the exterior cover, but there is also interior cover. In the middle, the air is compressed. And also we have one small idea I will try to present in the picture. Okay, yeah, here. In the top part, we don't need to actually take the direct sun rays, so we make this part not transparent, but this part can be transparent. So we close this part to protect interior. And here is habitat first habitat, and second habitat, and third habitat, and fourth habitat. This part in the middle between the habitats is for a greenhouse. It's for growing plants, vegetables, and so on. In the middle part, there is a mission area that can be used for the investigations and works and gym or other facilities. And one other idea is about having the design itself can produce its own oxygen from the carbon dioxide outside. It's like the MOXIE design, so we can put like some the machine of the MOXIE in this part, and they can take the air and press to this part, but it will not be stable. The air will be converted to the oxygen for the inside life. In the plan, it will be something like this. One more thing is about the lighting. Because we have like plants inside of this project, we have to have extra lights, because the Mars light is not enough. It's very weak. And as you know, in the greenhouse of the space, they use different lights, and each of it can be placed according to the plants. And here there will be pressed air. So if you have the pressed air, the light will be released around in a better way. And how we can increase our village? We can increase. It was the initial thought, but it was like very complex, and we needed to cut a lot. So then we have thought about two different options. It can be something like this and have only 4 opening, and it will be according to the growth of the village. It can be open or closed. And the second option can be something like this in order. And this is our project's render of the outside. And in the inside of it, as you see in the middle part, we have the mission area for, like as I said, for investigation and works, and maybe serving and gym area, and these are the habitats. So it can be designed for first mission, and then it can grow with the new doors. It can be opened from here. It is a very flexible project. And here is like the a house in the garden. This one another interior design, interior render. And next one, and the night view of the interior, and the night view of the other view, and this one also. And that's all about our presentation and project. Thank you. And you can keep contact with this email all the time and ask any other questions.